In this short video, we will take a look at the CrystalMaker 10 or CrystalMaker X software package, which is available for Windows 7, 8 and 10, and for Mac OS X from the Yosemite edition. CrystalMaker lets us build and visualize crystal and molecular structures in 3 dimensions quickly and easily. We can then output these visualizations as image files for reports, papers and dissertations, or even export animated videos for presentations. When you first launch CrystalMaker X, you'll be presented with the new library browser that you see on the screen here. This gives easy access to the examples and reference structure libraries that ship with the software. The window is divided into 2 vertical panes. The list of library folders over here to the left, and on the right, the icon view showing the contents of the selected library folder. For this video, I'm going to open the file for Corundum. Let's take a quick tour now of the user interface of CrystalMaker 10. If you've used CrystalMaker 9 before, you'll notice that things have undergone some serious changes. In the center of the screen, we see the graphics pane. This is currently displaying the crystal structure for Corundum, using these blue polyhedra to represent the arrangement of aluminium and oxygen atoms at the atomic scale. Each of these blue polyhedra represents an Al06 octahedron, highlighting the 6-fold coordination environment of the aluminium. I've set things up here to display 2 panels that are normally hidden by default. These are the structures list to the left-hand side and the log panel to the bottom. These can be hidden or added from the View menu at the top. The structures list only ordinarily appears when you have multiple structures loaded within one single file. The log displays the results of any screen tool operations that you perform, such as bond searches. The text that displays in this log can be copied to other programs if needed. Most of the controls you will need to use in CrystalMaker are located in 2 places. Firstly, along the main toolbar at the top of the screen, and secondly, in the tool strip that appears near the bottom when the mouse cursor is inside the graphics pane. You can click and drag to relocate the tool strip should you need. The currently selected tool is highlighted in blue. In this case, the hand icon, meaning that we can move the crystal structure manually by holding the left mouse button and moving it around. A key part of the software is over to the right hand side of the screen here, which is called the Inspector pane. This has a series of 7 tabs that allow you to manipulate the crystal structure that's displayed in the graphics pane. By default, the first pane that is shown in the inspector is this Info Inspector. This is split into 2 parts. The top is a rich text notebook that gives you information about the crystal structure or the material in question, while at the bottom we have an info pane with structural information such as the chemical formula, space group and lattice parameters. The second tab is the Atom Inspector. This pane allows us to change how the atoms are represented in terms of shapes, colours, whether they're visible at all or not, and whether they are labelled. We can also change the size of the atoms, and there's an information panel at the end that shows us the coordination environment, showing here, for example, that the aluminium is coordinated by 6 oxygens, while each oxygen is coordinated by 4 aluminiums. You can see at the moment that the aluminiums are represented by these solid rendered octahedra. We can change this view by clicking on to the polyhedra and selecting a different option from the window that appears. For example, we might select this translucent plus atom and bond cylinders representation, which will show semi-transparent octahedra with the aluminium atoms represented within those and the directions of the bonds coming from the aluminium to the oxygen. A red X, meaning that the oxygens are actually hidden at the moment, we could change this so that the oxygens are represented as spheres as shown here. The colours can be easily changed should you wish, and the legend within the graphic is automatically updated too. You can hide whole parts of the crystal structure if you need to, as well at this stage. The third pane is the Bonds Inspector. This pane lets you edit all of the bonding specifications for the current structure, as well as providing a coordination preview. It effectively combines the old edit bonding dialog in CrystalMaker 9 with the same program's bonds list for those that have used CrystalMaker 9. If you ever need to add a new bond, you can easily do this by right-clicking anywhere in the bond inspector and choosing Add Bond Specification. Once you've edited your new bond specification, you can edit its settings, including its from and to elements and the distance range that it searches for possible bonds. As you do this, the structure will be updated live on the screen and the new bonds and polyhedra automatically generated. The fourth tab is the Volume Inspector, which lets you add or manipulate lattice planes and volumetric data to crystal structures. For example here, showing a 111 plane running through our crystal structure. The fifth tab is the Model Inspector. Most of the settings that control your crystal structure's appearance are included on this pane. The Model Inspector lets you control the unit cell display, changing the line style and width that represents the crystal structure's unit cell. We can hide or show the axes showing the orientation of our crystal structure. We can change the default settings for any annotation labels that we add. And we can change general settings for how spheres, ponds and polyhedra are represented in the software. The sixth pane is the Rendering Inspector. This allows us to change for any structural model the way it's rendered on screen by editing the background colouring, the lighting, the reflectivity of the atoms and polyhedra, the degree of perspective and depth fading. These options can really change how a model appears, and not always in a good way. For example, the background by default is black, and this works really well on a computer screen. But if you're going to want to print your visualization as part of a report or dissertation, you're likely to want a white background, and this can easily be changed here. You can also choose and customize various other options which may be better suited for visual presentations, such as those in PowerPoint. The depth fading options can be particularly useful, but again should be approached with caution. Here, at the moment, depth fading is shown to be off. The small tick box here is not enabled. If I tick this, then it starts to add depth fading into the visualization, and you can see how the polyhedra and atoms at the back of the model are fading away a little bit because they're deeper in. We can change the degree of this effect by moving these red dots. At the bottom, we can also change perspective options, which again can dramatically change how a model is represented. Be careful with this, as it can distort the structure in an unrealistic fashion. So make sure you decide about the narrative that you're trying to tell. The final option is the Selection Inspector, and this displays information when we select one or more atoms, bonds or polyhedra in the crystal structural model. For example, if I click onto the arrow tool here and the tool strip at the bottom, I can then click on an atom and the information about that particular atom will be displayed over on the right on this Selection Inspector. You'll notice as I've set this corundum structure up that there's some floating atoms that aren't coordinated to anything. Of course, these oxygen atoms are connected to aluminium atoms, they're just not within the range that's currently displayed. We can change the range displayed using the range tool in the main toolbar at the top of the screen, but we can also use the zapper tool, which is this arrow in the tool strip, to click on atoms and remove those from the display. We then go back to the hand tool, we can rotate around a bit more, and that will highlight other atoms that need to be removed, and so on until we're happy with how our crystal structure is visualized. Once we've got a finished product that we want to get out of CrystalMaker and do something with, we can go to the File menu and click either Save or on a Mac Duplicate so that I can save this with a different name. From the File menu, we can also export graphics in various 2D formats or video in the form of a rotation movie. The final thing I want to show you is how to generate your own crystal structures, either by importing data from a database or by adding in crystallographic data manually yourself. The File menu allows you to open files with various different formats, for example CIF files from the ICSD, or refined crystal structures from GSAS and Topaz. You can also add in your own new crystal to generate a new crystal structure from information that you might have printed in a paper or been provided by a peer or supervisor. In this example, I'm going to generate the crystal structure for sodium chloride. The first thing we need to know is the space group. I'm not going to go into the details of what a space group is, but it's important that you realise that the notation used is very specific. For example, sodium chloride crystallizes in the space group FM*3M. These symbols, this space group, tell CrystalMaker where the atoms can be within space. If we're going to add this in, we need to type it in the proper format with spaces between each operator. And so in this case, FM*3M would be represented as this, with F as one operator, M as a second operator, bar 3 as one operator, the bar and the 3 together, the bar represented with a minus sign, and then finally the M at the end. You can see it's picked this up as space group number 225. A neat trick is that you can actually type in the space group number yourself, and it will automatically recognize the space group. You can also browse and look up different crystal systems, different lattice types, and find the space group in that way. Once we've put in the space group, we can enter the lattice parameters. For sodium chloride, those are 5.63, so the A, B and C axes are all 5.63 angstroms in length. We can then add in the atoms in the asymmetric unit. In this case, we need an extra atom because we need sodium and chlorine atoms, so we click the plus symbol at the bottom of the screen here. We can then click on the rows, click again, and edit the labels, occupancies, and fractional coordinates for the two different types of atom. In this case, we have sodium atoms, so we need to replace the silicon that's there by default. The occupancy is 1, that indicates that this crystallographic site is fully occupied by sodium and sodium alone. And then similar for the chlorine site, we need to represent that chlorine is fully occupying that site. We're quite lucky that the Cartesian coordinates for sodium in sodium chloride are actually 0, 0 and 0 in the x, y and z directions, and so we can leave this as it is. The chlorine, however, is on the 0.5 or a half 0, 0 site, and so we need to make this change in here. So this tells CrystalMaker where the atoms are in space. By using this information combined with the space group, CrystalMaker is able to then generate all of the atoms over an extended range. And then we click OK. And so now you see we've got representation for sodium chloride here. In this case, it's not chosen very nice colours. By default, chlorine is this kind of green, and the sodium is in this strange yellow olive colour. So the first thing I'm going to do is change that. I'll go to the Atoms Inspector, and I'm going to make the sodiums a nice red colour to make them a bit more obvious. And I usually like my chlorines to be blue, so I'm going to change those as well. Okay, much more appealing. Running through the top menu bar up here, we can see the axes representing the orientation of the view down in the left-hand corner of the screen. We can take this away by clicking the axes button. You can see the unit cell is represented with the white box in the graphics pane. We can toggle that on and off with the cell button. The scale button automatically resizes the visualization of the crystal structure to fill the graphics pane, and the center button makes sure that it's centered within the graphics pane. If you want to look at a particular orientation, we can click the Orient button with the eye icon, and this will allow us to look down certain lattice planes or on certain faces of the unit cell. And obviously we can also use the hand tool to manually move and rotate the crystal structure if we want. There's some other useful things that we can do while we're here as well. For example, to use the bond distance tool down here. And this will allow us to click on individual atoms or polyhedra within the representation of the crystal structure. So I clicked on the chlorine, then I click on the sodium, and it tells me that the distance between the sodium and the chlorine is 2.815 angstroms. A more advanced way of looking at this same information is using the distances tool. The Distance Explorer shows a representation of all of the coordination spheres within the local environment. And so we have this histogram at the top representing distances, in this case, from a chlorine atom heading outwards through the crystal structure. So we see our first nearest neighbour atom in sodium chloride will be the sodium, so we know that chlorine is coordinated by sodium. The next nearest neighbour will be another shell of chlorine atoms. In the bottom, we can also see that we have 6 of these sodium chloride bonds at 2.815 angstroms. This is telling us that our chlorines are octahedrally coordinated by sodium atoms. I hope this has been a useful video for you and that you enjoy using CrystalMaker. It's very hard to learn software through watching a video, however, And so it's really important that you just play with the software and see what it can do for yourself.